This video is going to hit the first part of section 10.2 in our outline. We're going to focus on the confidence interval for the difference of means. And just like we saw back in chapter 9, we're going to live with our good old friend, the t-distribution again. Why? Because we're going to be working with means, and we're going to go under the realistic assumption that we would have no idea what the population standard deviation is. And therefore, we're going to have to use the standard deviation from our sample as the unbiased estimator. And that'll be part of the sampling distribution of the difference of two means. So what you'll see in this, it's going to be a relatively short video. I'm just going to work through one example, but it'll cover the concepts you'll see in steps 9, 10, 11, and 12. To reiterate very quickly, we would love it if we knew our mean and standard deviation of the population, because if so, we could work with the true population standard deviations. We could compute a sampling distribution for x bar sub 1 minus x bar sub 2. These would be our two samples, our two means that we would compute. I'll use the one subscript and the two subscript here just to show the two different SRSs that are involved. And again, if we had the luck and we knew the true population parameters, we could also come up very quickly with the standard deviation of the difference of the two means. It would be nothing more than what? Standard deviation squared divided by the first sample size plus standard deviation of the second squared divided by the size of the second, and take the whole square root of it. Remember, variances, when you're adding or subtracting random variables, those variances always add. And when they're sampling, those variances will get reduced. That's all the things we talked about back in chapters 5 and 6. They'll get reduced by what? By the size of your sample. This would be wonderful. We could do our Z statistics and ride off into the sunset and be good. But again, what's the bottom line? We don't know those sigma values. All we can do is we can work with our sample standard deviations that'll come from our two SRSs. And so, as I said up here, let's be real. We don't know what those two things are. So what are we going to work with? Well, we'll come with a couple parameters. In our first sample, we'll call it x bar sub 1, sx1. The book will just call it s sub 1. I just like to show it as the sample standard deviation of the first sample. And then n1, our population. And then for our second random variable, the same thing. The book will just do s sub 2. I just like to do this sx2. It's just showing it's the sample standard deviation from the second random variable that we're working with in its sample. So what's the sampling distribution of x bar sub 1 minus x bar sub 2? Well, it's nothing more than mu1 minus mu2. That's what we would expect to happen in the real world. And what will our standard deviation be for? What's sigma for x bar 1 minus x bar 2? And it's what we've talked about in the prior chapter. We will take our two sample standard deviations, square each one, divide by the appropriate sample size, and add them together. And then what's the nice thing? Again, because it's an unknown standard deviation, we have to use our estimates through the two sample standard deviations. We can't use a normal distribution. We'll have to fall back to a t-distribution. And like everything else, we're going to need to see conditions being met. We need to have simple random samples. We need to meet the 10% rule when we are actually doing true sampling out of a finite population. We need to make sure with the 10% rule that assures independence of the elements pulled out in our sample. And it's what drives and what allows all these standard deviation calculations to fly as well. We'll also third be looking for an n, our sample size is bigger than 30. If so, it allows this central limit theorem to come aboard. And if our n value, our sample size, happens to be less than the square root of 30, we're going to have to fall back to the same thing we did in chapter 9. We need to do manual inspection. Make sure we see no outliers in our sample data, and we see no strong skewing in our sample data. If that flies, then we are welcome to work with our t-distribution. And specifically, if we look at it in the context of confidence intervals, here's what our interval is going to look like. It's going to look like x bar sub 1 minus x bar sub 2, plus or minus a t-value. A little bit more about that in a few moments. And then what do we have? Now I kind of went back to the book language this time. Sample standard deviation from the first sample, squared over n plus 1. Standard deviation from the second sample, square it, divide by n plus 2, add those two lovely things together and take the square root. So this t star times this, our standard error, that'll become our margin of error, the plus and minus that we'll do with this confidence interval. Now, here's the interesting thing. Well, interesting. Here's the challenging part. How do we figure out how many degrees of freedom to use? Well, there's two ways in which we're going to see where this comes from. They're going to be, in all honesty, slightly different. It all depends. If we're going to take a kind of a manual approach to do this, kind of like we've done in the past, we will use a conservative approach for our degrees of freedom. We will take the lesser of n1 minus 1, n2 minus 1. So in other words, look at your two sample sizes, see which one is the smaller, choose that, subtract 1 from that sample size, and you will have the degrees of freedom to use to calculate your t-value. Now, if we're going to do a precise calculator-based work, and that's something that we can do with a two-samp t-interval calculation, you'll see on page 640 a very complicated formula. You do not need to memorize or use that complicated formula on the AP exam, but it is the value that your calculator will actually use. So what we'll do as I work through my next example problem, we're just going to work with the good old conservative approach. I'll also show you how this would be done on a calculator. So that's kind of all our basics. It's very, very similar to what we saw in Chapter 9. Couple new wrinkles, but hopefully not that surprising for you to deal with. And so here's what we're going to do, just to kind of wrap up the rest of this video. I'm going to work with problem 7. It's an actual supplemental problem in the textbook. You see it as one of the check for understandings, but we'll go ahead and work it through here. It's one of the extra problems. It's not actually worked out in your textbook. So what we have is Department of Agriculture that does samples of average price of bushel of wheat from wheat producers. They took some simple random samples in both the month of July and September, and they got a sample price, a sample mean price for the two surveys that they did, and also they calculated the standard deviation of the associated sample, the sample standard deviation. In July, they surveyed 90 wheat producers. In September, they surveyed 45. And what we're trying to do is just build a 99% confidence interval for the difference in true wheat price from July to September. And I'm going to look at this. I'm going to go ahead and set my variables up as follows. And I'm going to move over to my paper here to kind of get us started. Once I find where I put that piece of paper. And here it comes, just in time. I'm going to focus on the random variable mu sub s minus mu sub j. I'm going to do September minus July. Could I have flipped it and done July minus September? Absolutely. And notice instead of 1 and 2, I'll just use s and j, a little bit more meaningful in the context of this problem. So I've gone ahead and built my parameters. Here's the mean for September, the mean for July, the sample standard deviation for the respective months, and the respective sample sizes in both go-arounds. What else do I want to check? Do I have SRSs in both? I sure do, according to the problem. Of the number of wheat producers that I sampled from, do I meet the 10% rule? Well, I have 45 and 90. Is it safe to assume there were at least 450 wheat producers around in this month, September? Yeah. Is it acceptable to assume there were at least 900 wheat producers across the country in July? I think the answer is yes. Have I met the 10% condition? I certainly have. And by the way, nice, central limit theorem can kick in for both of these. I got a 45 and a 90 for my sample size. I don't need to look at the raw data associated with these samples. I can assume some normality that applies here. Now again, what's the one thing I can't do? I can't work with a normal distribution. I need to work with a t-distribution. Why? Because I'm working with sample standard deviations, not the true population standard deviation. As soon as I venture into the unknown, I live with the t-distribution. So look at how I've gone ahead and structured the interval. You can see here's my x bar sub s minus x bar sub j, 361 minus 295. By the way, that'll become a 0.66 that you'll see a little bit lower down here. Here's my t value. I got to come up with that. And I've written out the formula for the standard deviation of the difference of the two sample means. 0.19 squared over 45 plus 0.22 squared over 90. Let me extend my square root just for sakes there. When I work that through the calculator, I'll have 0.0366. What's my t value? Well, degrees of freedom, I got two samples, 45 and 90. I'm going to take the smaller of that, 45, subtract 1. I'm going to work with a degree of freedom of 44. That's my conservative approach. Remember, in a conservative approach, I'm kind of giving myself a greater margin of error to work with. That's why we call it conservative. My t value, t sub star that I'll use is, well, what am I looking for? 99% confidence interval. So where do I need to get my inverse t value from? At 0.995. If I run my inverse t of 0.995, 44, I'll come up with a t star value of 2.69. And so what does my interval then start to look like? Well, 0.66 plus or minus 2.69 times 0. Let me fix this. 0. Let's get a pen that actually works. I got 7 million. Hopefully I got one. There we go. 0.0366. So 2.69 times 0. Holy cow. Don't you enjoy me with 7 million markers? Let's see if I can write the number so you can actually read it. Watch this. Look at that. 0.0366. I knew I could do it after about 19 tries. Sorry about that. So I hope you can see it. It's at least a little bit legible at this point in time. 0.66 plus or minus 2.69 times 0.0366. And what's that give me for my interval? The value is from 0.561 to 0.758. I'm 99% confident that the interval 0.561 to 0.758 captures the true mean for the difference in bushel price means from in September versus July. So I can see what the difference is. I know that's a positive difference. I'm assuming a positive difference. I'm 99% confident on that fact based on the numbers that I'm seeing. Now, we talked about that ugly formula. Let me just kind of bring that into play for you for a moment. And we'll come back with a slightly different answer. And you'll see why in a couple seconds. A two-sample t-interval test. Let's get the screen well enough. So, stat, test, and it'll show up two-samp t-interval. It's option 0. And look, I'm going to work with stats. And I've put in, first three fields that you see here is the data for September, a sample mean of 3.61, sample standard deviation of 0.19, sample size of 45. The July numbers, you can see 2.95, 0.22, 90. I'm asked for my confidence level. Good. One other question you're asked, is this data pooled? Yes or no? Please say no. Down the road, we'll talk a little bit more about pooled. We did that pooling a little while ago with the sample proportions. But what we're doing right now, just keep your pool off. And final choice, go ahead and calculate. And look what the calculator does once it gets around to doing all its chugging under the screens. It comes up with an interval of 0.56388 and 0.0756. Pretty close to the values we had, just a little bit different. A little bit, if you think about it, a little bit tighter. Remember, our degrees of freedom was kind of a conservative approach. And here's the interesting thing. Remember that ugly formula that you'll read about. Look how many degrees of freedom that said. It's 100. A lot more degrees of freedom. And so as a result, it does allow our confidence interval to get a little bit tighter. Not by much, but just by a little bit. So this walks through the process of confidence interval testing with the difference of two means. We'll do hypothesis testing in just a little bit. And we'll actually probably use this one problem as one of our examples.